All right, everybody, let's get the lecture going for this morning. Very good to see everybody here. How's everybody doing today? Did you guys all have a good bank holiday? Okay, so we've got another bank holiday coming up this weekend as well. So that's something. So today we're going to be kind of shifting gears a bit from some of the things that we've been thinking about over the past few weeks. You know, the past few weeks we think about nuclear physics, a few ideas about atomic physics, some ideas about photons and electrons, that kind of thing. So for the next few weeks, for the rest of the semester, we're shifting gears. We're going to be working towards thinking about Newtonian gravity and understanding orbits and understanding simple harmonic motion. But before we get to those topics, we're going to focus on today's lecture, which is about circular motion. Now, before we kind of dive into the physics, I've got an announcement for you guys. So we've got on Tuesday afternoon, we're going to have a seminar. So we've got a seminar coming up on Tuesday afternoon. Have you guys heard about this already? You guys been emails about this? Okay, so it's right here in the New Sciences building. Which room is this going to be in? So 03, so just down the corridor. So it's either going to be right after or right before the Tuesday workshops, depending on which workshop you're in. So I'd really encourage everyone, come along to the workshop and then head over and come along to the seminar. So it's by Dr. Vanessa Graber. She's going to be telling us about the physics of pulsars. So it's going to be a really exciting opportunity. So this is actually going to be a kind of research level talk, but she's told us that it's going to be accessible to students, and it's okay if you kind of don't get everything. Sometimes it's interesting to get a sense of the research that's going on. So we have that coming up on Tuesday. So I'm definitely going to be there. So we can just all head over after the workshop or head back for the next workshop. Now, there's actually a connection between pulsars and really all of the topics that we're going to be studying for the rest of the semester. So before we dive into circular motion, I just got a couple of slides to share with you guys a little bit about what's going on with pulsars, some of the physics involved there. So we've got this little animation here. So we've got this core here representing the pulsar, and pulsars are sometimes described as cosmic lighthouses. So these are really dense stars, neutron stars. So a star that's collapsed just forms an incredibly dense core, and it's emitting these radio beams here. And the neutron star is spinning unbelievably quickly. And what we see on Earth, if you point a radio telescope in the right direction, we occasionally see these pulses of radio emission due to the rotation here. So that's the kind of basic idea with what's going on with a pulsar, just in a animation. Let's take a look at some astronomical data kind of related to this. So this is a really beautiful image of the Crab Nebula, which is home to the Crab pulsar, and it's taken with the Hubble Space Telescope and also an X-ray space telescope. So a really beautiful image, and the pulsar sitting in the center of this nebula here. Now, pulsars, really important topic for astrophysics, but they also really encapsulate all of the topics that we're going to be thinking about over the next few weeks. So at the end of the semester, we're going to be thinking about gravity and orbits, so obviously very important in forming the neutron star. Now, neutron stars, they're actually one of the most precisely periodic objects in the universe. You can actually use them. They've been described as cosmic chronometers because they rotate with such a precise period. You can actually use them to time things. And that periodic motion, we're actually going to be learning about periodic motion next week when we're studying simple harmonic motion. But key to understanding simple harmonic motion and understanding orbits, all this stuff that's coming up, is understanding circular motion, which is what we're focusing on today, and also very important if we're thinking about what might be going on in a neutron star. Now, who's studied a bit of circular motion before, maybe in some other physics courses? Okay, so a few people Not too many. Okay, so if you have seen some circular motion before, some of these things might be familiar. But what we're going to be thinking about today is not just understanding the concepts for circular motion, but also building that connection that we're going to need to be understanding simple harmonic motion. So that's the plan for today and where we're going to be going over the next couple of weeks. So let's start with a kind of fundamental question thinking about circular motion. So we've got this diagram here. We've got a car driving around a roundabout. So the car's going this way round. So what we're thinking about in this question, if the car's driving around the roundabout at a constant speed, what's the direction of the acceleration for the car in this question? So I'll just get the question going. We'll see what everybody thinks for this one. If you have studied circular motion before, maybe you remember this, maybe this is going to be a fairly simple question. If you haven't studied circular motion before, you don't need to guess, because remember, acceleration, it's how much the velocity is changing. So think about where the velocity is, think about the direction that's needed to change that velocity to get the car driving around the circle. That's going to tell you the direction of the acceleration. Okay, very good to see those responses coming in. Let's take a look. What does everybody think? What's the direction of the acceleration? What's everybody think? Okay, nobody going for option D, but we're kind of people thinking it could be A, B, or C. So let's take a look. Let's see what's going on with this car over here. So we got the car, and it's driving this way round. So its speed, its velocity, it's currently in direction B. So direction B is the direction of its instantaneous velocity. So obviously it's not driving in direction D, nobody going for direction D. So I can see why people might have been thinking for, maybe it's kind of option B, but that's the way the car's currently going. So that's its current velocity, but it's not going to keep on going this way, because otherwise it's not going to be driving in a circle anymore. So we've got to think about how this velocity is changing. That's going to tell us the direction of the acceleration. So at the current moment, the velocity is over here. Let's have a think what's going to happen to the velocity. So as we're driving around the circle, the velocity is going to be changing in this direction. So it's always going to be moving in this direction towards the center of the circle. So the correct answer is option C over here. So very well done, everybody who gave this question a go, especially if you got that it's option C. Now, this can be a bit counterintuitive because I guess how many of you, if you've been like a fairground ride or something and you're kind of swirling around and you kind of feels like you're being pushed outside? Well, that's because the ride is always moving in towards the center, and that's what you're feeling. So even though we might think intuitively, about things in circular motion, they're getting kind of flown out towards the outside. If we look at how things are actually moving, the velocity, it's always changing, it's always pointing towards the center. So very well done, everybody, with that question. Now, that's the direction of the acceleration, but we can actually get a bit more exact, get a bit more quantitative. So suppose we know the speed that the car's driving around the circle, and we know the radius of the circle. Let's have a think in this question. How can we actually calculate what the acceleration of the car has to be? So we've got a few different options here. Have a chat with the people around you, see which one of these has to be the relationship between acceleration, speed, and the radius of our circle. Again, with this one, if you've studied circular motion before, you might be able to remember this. If you haven't studied circular motion before, you don't need to guess. The key to this one is thinking about the units. Have a think about the units of acceleration, and then have a think about the units of the speed and the radius. And then how can you combine those units of speed and radius to give us the acceleration? There's only one way to do it. That's going to tell us the relationship between speed, radius, and acceleration. Okay, very good to see those responses coming in. Let's see what everybody thinks. Let's have a look here. Okay, so nobody's going for A and D. People seem to be split between B and C. c. So we're thinking it's got to have a squared in there somewhere, something like that, but just one of them. Now, this might seem like a bit of a tricky question, but you really don't need to guess with anything in this question. Let's take a look at what's going on here. So we've got our acceleration. So what's the units of our acceleration? Meters per second squared, exactly. Meters per second squared. And it's really this per second squared which is the key to unlocking this. So we've got our per second squared. Now, of the other quantities, what's the only one that's got any time, any seconds in it? Yeah, exactly. It's only the velocity, the speed. So the radius doesn't have anything to do with time. So if we think about the units of our speed, that's meters per second. So we know our speed is going into it, and our speed has units of meters per second. And our acceleration has units of meters per second squared. So the only way we can get this per second squared, we have to have our speed squared. So let's have a look at the units of our velocity squared. Velocity squared. So the units of that, we're going to get meters squared and then per second squared. So that's really good. We're kind of nearly there, right? So we've got our per second squared that we're going after. And the key thing is that this is the only way we can get our per second squared. So you don't need to guess, you don't need to kind of just try things, see what works. We know that this is the only way we can get our per second squared. So v squared has units of meters squared per second squared, but our acceleration is just meters per second squared. So how can we get rid of that extra factor, the meters squared, just get it to meters? Any thoughts? Divide by meters, exactly. So if we have v squared divided by the, well, actually it's the radius, isn't it? Divided by the radius, the units of that are going to be meters per second squared. So that's going to be the units of the acceleration. So very well done, everybody, if you figured that one out. But the key thing that I want to emphasize with this is that by thinking about the units and how we have to combine the units, we don't need to guess. So maybe if you're in the exam and there's a question about circular motion, you can't remember, it's the v squared over r, you can figure it out yourself, okay? And that's why units are so important, why it's always really useful to think about them. So the one last thing about this equation here, so we've got the correct answer, so v squared over r. What's going on with the minus sign here? Why do we have a minus sign on the acceleration? Any thoughts about that? What's the minus sign doing for us? So the idea here is if we're increasing our r, so we're making positive distance, remember the direction of that circular acceleration. It's always towards the center of the circle. So our acceleration is always pushing us back towards the center, and that's what the minus sign is doing. So that's what's keeping us going in a circle instead of flying off. So don't forget the minus sign. It's very important. That's what's going to keep you going around in a circle. So if you want an equation for your notes, correct answer, option B, good one to put a box around. Okay, really important equation. So I thought we might take a numerical example, see how this works in practice. So suppose we've got a car driving around a curve, and the radius of curvature is 70 meters. And the car's going to slide off if the acceleration is more than 6 meters per second squared. So let's have a think about this. How fast can the car drive into this curve without sliding off the edge? Okay, so we've got all the pieces we need. Have a think about this. Maybe check with the people around you. Let's see how fast this car can drive around this curve. So remember my tip with any numerical questions, I'd always suggest rearranging the equation for the thing you're interested in before substituting in any numbers. So here we're interested in the speed v. So what I'd suggest, rearrange that equation for v before substituting in any numbers, then sub the numbers in, see what you're going to get. Good to see those responses coming in. Let's see what everybody thinks of this one. How fast can our car drive around this circle here? Okay, nobody going for option D. Some people think it could be A or C. So what I suggest, remember with this one, any numerical question, it's always very useful to rearrange before substituting in any numbers. So in this case, we're solving for the speed, so you want to rearrange for that. But, maybe if we were working out some, maximum radius, then you might want to solve for that. So I'd always suggest do the algebra first, then substitute the numbers. That's going to make life much easier for you, like on the exam or anything like that. And when you do that, substitute the numbers, what do we get here? 20 meters per second. So that's how fast we can go into the curve safely without, sliding off, okay? So very well done, everybody, with that question, especially if you've got, that speed of 20 meters. Now, that's the basic idea with how speed and acceleration are related to the radius of our curvature. And this concept is going to be really important when we come to think about orbital mechanics and how orbits work, so satellites, all that kind of stuff. But for today, the thing that I'd like to be thinking about kind of connects a bit more to what we think about with, pulsars at the beginning of the lecture. So we've got the speed that we have going round a curve there. But sometimes it's useful to relate our acceleration and our radius to the frequency that we're going around a circle. So, if we've got like a car driving around a roundabout, naturally it makes sense to think about the speed of the car. But if we have things spinning like a centrifuge or, a neutron star, it makes more sense to talk about the frequency with which something is spinning. So in this question, we're just doing a bit of algebra here. So let's think, if we have something going in circular motion, how is the speed that something's going in that circle related to the frequency, so how many times per second it completes that circular path? So just a bit of algebra with this one, see how you get on. We'll take a look at the results in just a moment. We're just doing a couple of steps of algebra with this, hopefully a couple of very familiar equations by now. So our speed, distance over time, frequency is 1 over time. The one thing you might have to think a bit about this, we think about circular motion, so just substitute in what that distance is going to be when we're traveling in a circular path. So work through the algebra, see what you get for this one. We'll take a look at the responses in just a moment. Okay, let's take a look at the results. Let's see what everybody thinks for this one. Okay, so nobody going for D. Some people thinking could be B or C. Looks like most people going for option A. Now, whenever we're doing these kind of questions, don't try and do the algebra in your head. It's very easy to get something back to front, get something the wrong way round. Now, starting with this, we've got our speed is distance over time. Our distance, so it's the circumference of a circle, so 2 pi r. And then when you substitute that all in and you work through the algebra, we get option A over there. So very well done, everybody, with that question. We got the relationship between the speed we're going around the circle and the frequency. Now, this is really useful if you have any kind of circular motion where it's going around, more than once a second. So if you've got a centrifuge and it's spinning at 50 hertz, you can use this to work out how fast something's going in your centrifuge. But in the example of, say, a centrifuge, we're not so interested in the speed that it's spinning around. We're really more interested in the acceleration, so how much force we can get. That's typically why we're using a centrifuge. But we've now got these two really useful pieces of the puzzle to be thinking about here. So we've got our relationship between speed and frequency. And then from a couple of questions ago, we have our relationship between speed and acceleration. So in this question, let's see what we get when we combine these two. So what do we get for our acceleration in terms of our frequency when we use that relationship for the speed that you guys just figured out? With this question, you don't need to guess if you haven't seen this before. Just work through the algebra, just take it step by step. We know our acceleration minus v squared over r. We know our speed is v's 2 pi rf. So we're just making that substitution for the speed, work through the algebra, and let's see what we get for our acceleration in terms of our frequency. Okay, let's take a look at the responses. What have we got going on here? Okay, so nobody's going for A and C. Some people thinking could be B. Looks like most people go for D. Now, this can be a bit tricky, especially, we've got the pi's and the f's everywhere. But when you do the substitution, when you work it through, what we get here is option D here. Okay, so our acceleration minus 2 pi f all squared times r. So very well done, everybody, with that question, especially if you got that it's option D. Okay, so what this question tells us is if we have something spinning in a circle and it's spinning with some frequency f and the radius of curvature of the circle is r, we can work out what the acceleration is. Now, this is actually kind of quite a interesting result, okay? Because what this allows us to do, we can simplify this a bit. So, do you guys remember from a few weeks ago we were thinking about generators and the frequency of generators? So, almost always in physics, whenever we're thinking about things, especially spinning in a circle with some frequency, the frequency always appears with a 2 pi in front of it. I think we almost always see that. And we see that so often that we define this thing angular frequency. So it's just 2 pi multiplied by our frequency. And this actually is kind of a useful simplification, makes our life a bit easier. So with this question, we're just doing a bit of substitution, hopefully just a bit of easy algebra. What do we get for our acceleration in terms of the angular frequency? Now, angular frequency, that still might seem a bit of a kind of esoteric concept. Maybe, we preferred good old regular frequency. But in this question, we're just doing a bit of a substitution, just doing a bit of algebra, and it actually makes our equation for the relationship between acceleration and radius a bit simpler. All right, let's take a look at the responses over here. Let's see what everybody gets for this one. Okay, so no one going for C and D. Now, thank you for pointing out, just spotted, we're actually missing the minus sign in front of all of these. So all of these, they should have a minus sign. Thank you for pointing that one out, okay, the direction of the acceleration. So yeah, looks like when we do the substitution, so our acceleration, 2 pi f all squared times r, our angular frequency, 2 pi f. So we do the substitution and we get option B. Okay, so very well done, everybody, with that question. Hopefully just a bit of algebra. Now this is actually a very important equation whenever we're thinking about this kind of motion, because this is actually a very neat relationship between the radius and the acceleration. And all the stuff that's going on, it's all wrapped up in this angular frequency. So if we have something spinning at 100 hertz or a neutron star spinning even faster, we can have this relationship between, say, the size of that neutron star and what the acceleration is going to be in the crust. So if you do come along to the research talk on Tuesday, hopefully you can kind of see how some of this extreme physics really plays out. Now, for the last couple of slides for today, I just want to see how this kind of relationship works a bit kind of diagrammatically and set us up for next time when we're going to be thinking about simple harmonic motion. So we've got this diagram here. So we've just got a little object and it's going to be going in some circular motion. So, this could be a car driving around a roundabout, could be a planet orbiting a star, could be a satellite orbiting the Earth, anything undergoing circular motion. And we've just got its coordinates here. So as it completes, one orbit, going to trace out a circle. Let's just have a look, though, at what's going on with one side of this motion here. So I've got, what I'm calling the x-coordinate. You might think it would make sense to call this one the y-coordinate, but the convention is it's just called s. So if you look in your textbook, they call this side s. Whenever we're thinking about this kind of motion, is called an s. So that's just what we can work with here. So let's see how s varies as this little object completes one circuit. So we've got this little diagram here, we've got time on this axis, and we're just plotting what s looks like on this axis. Now, if you're following along in your notes, you might want to draw a little sketch, see what you think the s coordinate's going to look like. Let's have a look as we send s in an orbit, what it's going to look like. So as s goes round and we're just tracing out this position here, what do we get here? We get this nice curve over here. Now, does anybody recognize what kind of curve do we have over here if that's starting from 0? Any thoughts? Yeah, it's cosine, exactly. Very good. So what this tells us, this is our kind of think about it as vertical, even though it's not really vertical. But this is one aspect of that circular motion against time. So do you guys remember last semester we were thinking about the motion of waves, and if we had sinusoidal, so it could be a cosine or a sine, and we could work out the relationship between the velocity and the acceleration. So we can actually do this same kind of idea here and also connect it to that equation that you guys just found. So we had this equation, we got the minus sign in there, so that's how it should look with the minus sign. So you guys just saw that whenever we have circular motion, our acceleration minus omega squared s. So remember, so that s, that's going to be the radius of what our circle is. So let's have a look what our acceleration looks like versus time. So now we're plotting our acceleration, and we get this curve over here. Now, what kind of curve is our acceleration versus time? Can anybody spot what kind of curve that one is? Exactly, so it's just a minus cosine. So if we put a cosine into our position versus time, so then we get a minus cosine. So that satisfies the equation that we have up here, where our acceleration is equal to minus something times this position over here. So whenever we have anything which is undergoing this kind of motion, so where its position is just oscillating between here, and we have this relationship between position and acceleration, that's actually what we call simple harmonic motion. So whenever we have something just swinging backwards and forwards, that's what we mean by simple harmonic motion. And you can think of simple harmonic motion as we're just really projecting one axis of something undergoing circular motion. So if you imagine this little point here just swirling round and round, and we're just looking at this position here, that's what we call simple harmonic motion. And this is a really important kind of motion. Whenever we think about it, it's an unbelievable range of things that it applies to in physics. Now, before we wrap things up for today, I just have one last slide to share with you guys, because you might think, okay, well, this is a kind of niche situation. We've got the acceleration, we've got the that angular thing squared, and we've got the s. Okay, but just the last thing, because simple harmonic motion, it's just used all the time in physics here, and I thought it was really kind of nicely summed up in this tweet here. Now, I know this is all going to kind of age this whole thing terribly, but basically, we've got physicists, literally absolutely anything. Is this a simple harmonic oscillator? So as we're going to see, simple harmonic oscillators, physicists just use them over and over and over again, and anything that you point at, and you might think I'm exaggerating, but I'm really not. Physicists will say, okay, well, maybe we can model that with a simple harmonic oscillator. So it really is a super, super important piece of your physics toolkit. That's what we're going to be focusing on for the next lecture, okay? So just a couple of very quick announcements. Remember, so another bank holiday, so no lecture on Monday. I see everybody in the workshops on Tuesday, and then we can head over to the seminar. So hope you all have a fantastic bank holiday weekend, and I'll see you guys all next week.